everyone. Thank you for joining us today. Thank you for your patience. And welcome back to the MOFspace webinar series. As is our tradition, I would like to remind you that this series is a part of EU4MOFs Cost Action, and our main mission is to bring together experts and researchers in the field of metal organic frameworks and other porous materials. You can find more information about our action on our website and follow us on social media. By the way, we have a YouTube channel, so you can subscribe to our YouTube channel and watch all previous recordings from the previous webinars. Okay, with that, I think we can go closer to the topic of our today's lecture. And today's webinar today we will hear about how post-synthetic modifications of MOFs can help develop photo and piezocatalytic systems for water and carbon dioxide reduction. And our today's speaker will help us with that. So now it's my great pleasure to introduce our speaker, Professor Tapas Maji. So he is a professor and chair in the Chemistry and Physics of Materials unit at the School of Advanced Materials, Jawaharlal Nehru Center for Advanced Scientific Research. He is also an associate faculty member of the International Center for Materials Science and the New Chemistry unit. Professor Maji received his Master's Science degree in Inorganic Chemistry from Burdwan University in 1997. Followed by his PhD from the Indian Association for the Cultivation of Science in 2002. He then carried out postdoctoral research at Kyoto University in Japan from 2003 to 2005 under Professor Susumu Kitagawa, who received the Nobel Prize in Chemistry last year, yes, for the development of MOFs. His research focuses on the synthesis and structure property relationships of functional MOFs and porous organic polymers for a wide range of applications, including carbon capture, cost-effective separations, green hydrogen production, carbon dioxide conversions, and atmospheric water harvesting. Professor Maji has received numerous prestigious awards and recognitions, among them the Bronze Medal of the Chemical Research Society of India and the Materials Research Society of India, the Scopus Young Scientist Award, the Clarivate India Excellence Research Citation Award, and the Senior Alexander von Humboldt Fellowship in Germany. He is a fellow of the Royal Society of Chemistry, the Indian Academy of Sciences, and the World Academy of Sciences. He has also served as an associate editor of ACS, Applied Materials and Interfaces, and is currently a member of the editorial boards of several leading journals, including Angewandte Chemie, Dalton Transactions, ACS Applied Energy Materials, and Inorganica Chimica Acta. With around 300 research publications, Professor Maji has made outstanding contribution to the field of functional porous and hybrid materials. We are really happy to have you here with us today. Thank you very much for joining, for accepting our invitation. And now the floor is yours, please.
So at the outset, let me thank Alicia, Evelyn, and Stefan for this invitation. It is a privilege, and I'm extremely happy that I got this invitation, and I want to share some of our research work, what we are doing in the field of metal organic framework. So this webinar series, as I heard, it is very, very well network throughout the Europe, and leading scientists give their presentation in this platform. So I am extremely delighted and happy to be get invitation and want to share some of these results. So today, what I'm going to talk about, just some recently what we are trying to do, developing particularly the some of this catalyst by post-synthetic modification of this metal organic framework for the energy conversion. So all of you know this today's world is seeing a very critical transition, particularly in the field of energy and environment. And so when that there is a significant amount of the carbon dioxide in the atmosphere, the concentration is above 420 ppm. So, and it is that that global warming and their catastrophic effect showing us throughout the world. So, we need that carbon mitigation or the carbon utilization is the paramount important. At the same time, that energy transition from the fossil fuel to some kind of the renewable sources is also very much paramount. So in my presentation, how we can tackle such kind of problem, I'm going to share some of our results. So before that, all of you know that metal organic frameworks has been shared the Nobel Prize last year, and these three gentlemen, Professor Susumu Kitagawa, Professor Omo Riyagi, and Professor Richard Robson, they received this prestigious award for the development in the field of metal organic frameworks. Okay, and I had the privilege to work one of these, as Alicia mentioned, that we worked with Professor Susumu Kitagawa 3 years during my early stage of the after my doctoral degree. So I spent 3 years with him in Kyoto University, and I'm going to dedicate this talk to this Professor Susumu Kitagawa. Okay, so so all of you know this, that this metal organic frameworks is the very important materials. And in my group, we are working particularly looking at the synthesis characterizations and their different functionality, particularly the MOF. We are looking at the energy storage, particularly the small hydrocarbon storage, and the absorptive base separation, carbon capture, separation and neutralization, and different type of the nanoscale of metal organic framework for different applications. So we also work on metal-free system, particularly the covalent organic frameworks and conjugated microporous polymers for their versatile applications. Particularly, we are using these materials as a host material for stabilizing the single atom catalyst for different type of electrocatalytic application, which I'm not going to talk today. And one of the issues of the MOF is the processability. So in my group, we extremely work that how you can make the processable material by using that low molecular gelator. This low molecular gelator can be connected, like let's say one example I want to give, porphyrin. When you connected with this alkyl amide chain, like the tarpyridine based alkyl amide chain, and you have these 4 metal centers, and you can bind. And when you bind the ruthenium kind of metal ions, so you can get the coordination polymer gel, or some sort of, you can also say metal organic hybrid gel. Such gel can be utilized particularly different application, stimuli responsive, optoelectronics, and the catalysis you can do. So, and also you can have this MOF or POP based heterostructures, particularly that interfacial electron transfer is very, very important. You can make the type 2 heterojunction for like the different type of catalytic application. So in this one examples, we have recently published in Anglo Chemistry that it's a COP, and you find the topological insulator like lead bismuth telluride. So you can make such kind of, this kind of topological insulator can replace the platinum as the electron sink. And because of the presence of the 6 s2 lone pairs in the bismuth, it can use for the catalytic side to binding the CO2. And here in this work, we have shown that it can be useful, particularly the syngas production from carbon dioxide and water. So these are the 4 subgroups in my group, and these are the 4 different type of materials we have been working last 20 years, and we have done some contribution in these fields. So let's start that. I don't think so we need the basic introductions of this audience. So however, this I'll try to give some sort of that. What is the MOF? All of you know, this is the class of crystalline polymers which forms by the interconnection of the metal or metal oxoclusters with the organic, different type of organic linkers. Okay. So this can be the metal or the metal clusters like this, like the metal nodes, single nodes, or it can be the paddle wheels or different type of geometry, even the linear chain. And you can synthesize different organic molecules, diatopic to tetratopic, or then you can get the versatile structures. So let's say if this kind of geometry depends upon the metal ions, all of you know that, let's say the diamondite structures, you can get the copper 1 or zinc 2 with the D10 electronic configuration, or the silver, you have this coordination number 2. You can connect that, you can get the linear coordination polymers. But when you take the copper, nickel, or the iron, which has the coordination number 6, you can get the three-dimensional structures. And these three-dimensional structures have the different type of network topologies, like some of the representative MOFs, MOF5, IR MOF74, or PCN22. So these are the material is the highly crystalline, extensive porosity, high surface area, and tunable structures with high stability and the possessibility. So these are some of the synthetic technique for preparing this kind of wonderful materials. You can do this in diffusion synthesis or solvothermal synthesis, microwave synthesis, and mechanochemical synthesis, electrochemical synthesis, sonochemical synthesis. But some of this, the pre-synthetic approach has been used to construct the tailor-made MOFs, but with rather restricted functional group scope limited by the typical MOF hydrosolvothermal synthesis. And some of the functional group in the pre-synthetic approach may not be compatible with the high pressure and temperature condition in solvothermal reaction. So then the post-synthetic modification is the wonderful way you can make the new material. So one of these, that if you have the metathesis, let's say where the metal ion can be completely replaced or the partially replaced, you can get the heterogeneity, or you can prepare the multivariate MOFs like the binuclear or the bimetallic, trimetallic, and complete exchange. You can get the new MOF, which is not possible to crystallize by the direct synthesis way. Or you can do some sort of the ligand exchange, again that partially or fully you can get the new materials or new MOF, or you can introduce the new functionality in the system, or you have this post-synthetic modification or introduce the new function by, let's say, some sort of you can put some metal binding sites and other way by post-synthetic modification to get the new functional group. Or the complete exchange of the guest molecules, that small or large, you can get the different type of that properties you can introduce. Okay. So these are the way you can post-synthetically, you can make it. Let's say my today's talk, I want to talk particularly in the photo or piezoecatalytic or photopiezoecatalytic, the energy production or CO2 reduction to some sort of the conversion to the valuable chemicals. So let's try to understand the basic principles of the semiconductors or photocatalysis. So let's say you have the semiconductors. When you put the incident light, which is the greater than the band gap of the materials, you can create the hole and electrons. So this hole and electrons simultaneously you can use for the oxidation, or you can use for the reduction using the electrons. But if you want to use the electron alone, you can you can use some kind of scavenger, either hole scavenger or the electron scavenger. You can use the half reaction. Okay. So then let's say that what is that the challenges behind the CO2 reduction. When you consider the CO2 reduction to the different product, particularly that CO2 to formic acid, if you consider the different reduction. So this is the reduction potential is minus 0.61 volt, or let's say CO is minus 0.52 volt. But if you look at the higher reduced products like the CH4 or the acetic acid, that the reduction potential significantly drop. So this means that in thermodynamically, you can get easily the higher order reduced product. But if you see the number of electrons involved in that CO2 to, let's say, methane or the acetic acid is high. So that means that kinetics of the electron transfer will be much faster, or the electron density during the reduction process has to be much higher to get the higher reduced product. Okay. So you can use the different type of sacrificial agent like water, amine, and the sulfides. So when you consider these are the preliminary step, so you have the light absorption, then you have the charge separation, CO2 binding, redox reaction, and the desorption of the product. These are the elementary steps for doing this kind of the catalytic process. So how it will be the useful in particularly the metal organic frameworks. So metal organic frameworks have the several advantage, particularly when you have the permanent porosity. It allows the accessibility of the catalytic site based on the facile diffusion of the substrate to the catalytic sites. Either you can have the tunable structures of the light absorption, and it is possible intra-bond the charge transfer or intra-space charge transfer, through bond charge transfer, different way you can say. Where the ligand can be the light harvesting moiety and your metal can be the catalytic site. Or this you can create the defect in this case, and when that you can create in the defect in the structures, that is very, very important, particularly that you can create the unsaturated site which can bind with the CO2 or different substrate during the catalytic process. Or because of the permanent porosity, you can insert that some sort of photosensitizer or the co-catalyst. So all this process, I show you, I try to give that some one of each example, how this the permanent porosity or that post-synthetic modification or the metal ion or the linker, it can change and you can get the different product. So MOF 808. So my next whole talk will be the one material. This is the MOF 808. So all of you know that after the discovery of particularly the UIO 66, there is a paradigm shift of the MOF research. Because these zirconium clusters, when it is connected with the oxophilic, this oxygen and the OH group, this form very strong SBU. This SBU can be connected with a different type of ligand and forms the highly chemical and chemically and mechanically robust structures, as well as that it can be the highly pH stable. Okay, so this zirconium 4+ in the higher oxidation state, these are the oxophilic and it can be very stable structure. So now this is the very interesting MOF. So if you look at the structures, so there is the two different type of pores. It is the 1.6 nanometers or 1.9 nanometer. That is the large pore, and it is the tetrahedral pore 0.8 nanometers. If you look at the secondary building unit, there is a zirconium 6, mu3O4, mu3, and there is a 6 format group which connect that between this between the cluster like this here, and then it is extended by the BTC ligand. And based on the synthesis condition, you can either create the mesoporosity by creating defect, linker defect, or you can have the complete microporous framework, where is that formula will be like the 6, 2 BTC and 6 format. So, and that the interesting thing about this material, particularly the MOF 808, it can allow the post-synthetic modification by the different way. So either that you can have the pre-synthetic modification, one of the zirconium clusters, you can replace with the some sort of the transition metal ion. So you can create the bimetallic secondary building unit, or you can, after because of the presence of the hydroxo and the oxo group, you can put some kind of the post-synthetically transition metal ions. And I will tell you why it is so important. Or this format linkers, you can just replace some of these different similar carboxylate group where you can attach the different metal ion after the post-synthetic modification. I'll try to give some of this example. And the whole process of the post-synthetic modification, you can process by the NMR studies. How many? So you have this format and the BTC ligand ratio when you dissociate this MOF complete decomposition. So then how the post-synthetic modification is happening, you can easily follow. And these are the very small particle size. You can 500 nanometers, even you can get below 100 nanometers of this, you can get this particle. So this will be the highly processable materials. Okay. So these are the several advantages. So that has give the wonderful platform to get the different type of functionality you can introduce. So one of this drawback, particularly the UI66 MOF for developing the catalysis. Let's say it is that is the theoretical paper. If you look at the one to the use as the light or catalyst, so this BTC linker or that the BTC linker, benzene dicarboxylate, it does not absorb light in the visible region. And then if you want to use the metal clusters as a catalytic site, but unfortunately the LUMO level is high compared to this kind of the organic molecules. So then the electron transfer from here to the catalytic site, it is not possible. If you look to the zirconium, hafnium, thorium, titanium, uranium, only the cerium, it is possible indeed from the LUMO because of the 4F0 low line molecular LUMO level. Okay. So now this way, so how you can use this very stable nanoscale MOF as a wonderful platform, and you can starting for the post-synthetic modification to get the different type of catalytic, you can engineer the catalytic material. So let's come to the first examples. So we have taken this MOF 808 and how you can impregnate or introduce either molecular light harvesting moiety and the molecular catalyst, which can use, and you can use that wonderful platform by the post-synthetic modification to use the study the CO2 reduction in aqueous medium. So this is the MOF 808. This is the zirconium MOF 808. So now what we have done, as I told you, there is a 6 or format group or 5 format group here, which is connected in the SBU. So now I have taken the same functional group that I have the solvent assistant Sally linker exchange. So now I have taken this kind of molecules which can connect, and it has the metal binding site. Okay. So now I have photosynthetically modified, and there is each I have exchanged the 3 or 4 kind of from the secondary building unit format. So now it is the covalently attached here. So in our design, so when you connect the ruthenium bipyridyl Cl2, so you can see the ruthenium bipyridyl you can connect, which can be the light harvesting moiety, because based on that, it shows wonderful. It is well-known material that it shows metal to ligand charge transfer in the visible region. So after that, you can keep one of the free bipyridine here. So this free bipyridine, either you can take the molecular catalyst based on rhenium or the manganese. So now you have the integrated catalytic system. So ruthenium, so now, so what we thought, either this from the ruthenium, the electron transfer can happen to the zirconium cluster, or because of the close proximity inside the pore, from there, this ruthenium, this electron transfer can happen to the rhenium side, and it can do the catalytic activity. So then all the characterization we have done, which I am not going details here. So this you can see that your means the crystallinity remain intact, and when we have photosynthetic modified, that the surface area simultaneously it is decreased. Okay. So this is the small size that this particle size around 250 to 300 nanometers. And when we photosynthetically modify, you can see the ruthenium d5 pi star bipyridine transition in that, which comes in the 460 in the visible region. Okay. So now when you can see that emission is coming at the ruthenium site, when and the WEP quantum is around 7.8%. And when we introduce further rhenium, and then you can see the further surface area decrease, and we can also get the rhenium MLCT band. Okay, and this is the high resolution TM, which is showing that 1.67 nanometer, which corresponds in the pore size. So now when we perform the lifetime of this is very surprising to us. So ruthenium bipyridine, when in the molecular state, is the lifetime is 185.5 nanoseconds. But inside the pore, the lifetime significantly increased, around 400 nanoseconds. So now this molecular catalyst, when in the solution state, because of the collision, okay, or the thermal vibration, that opens up the different non-radiative pathway. But when you can confine these moleculars, you can stop that because of the confinement effect, that you can stop the thermal vibration, it opens up the radiative pathway, and that's why the lifetime significantly enhances. But when you put the rhenium or the manganese, the lifetime significantly decrease because of this possibility of the electron transfer. So this is from the MOFspace analysis that we have done the band energy levels, and it is this indeed possible that it can do the CO2 reduction, either CO2 or different other product, which is the reduction potential is less than minus 0.63 volt. And LUMO level is also said that it is possible to do the water reduction. So this way we have done this electron transfer, that it is also that from the LUMO to the rhenium or bipyridyl, this electron transfer indeed possible. So then we have performed this CO2 reduction. Particularly, we have looked at the water medium, just water, only the sole water medium, and we got the not highly efficient activity, 1.5 millimole per gram, and that but the selectivity is very high. Okay. So then we have changed to that different kind of sacrificial agent, that BNAT, like 1-benzyl 1,4-dihydronicotinamide. So when we have seen that it has enhanced the activity, particularly CO, we got some amount of the CH4, the selectivity it decreased. Okay. So then our catalytic activity it increased here. So then also we done in the sunlight, direct sunlight medium, so that it is of course the weather dependent, and it is equally active. We have done the 6-hour time. So then we try to understand this mechanism, that how it is happening. So when you just take this kind of the sacrificial electron donor, and when with the titration, emission titration, we found in presence of that the emission intensity is decreasing. So this suggests the reductive quenching mechanism. But when you take the titration in the rhenium, that emission did not quench. So it is that suggests this is for not the oxidative pathway, it is reductive quenching pathway. And photocurrent measurement and the impedance measurement, it suggests in presence of light, there is a significant amount of that charge separation happens. So then we try to understand that how this mechanism, because this is very important to know. And CO2 to CO is the 2 electron reduction process. First, it will go to the CO2 to CO2 star, CO2, the electron plus H plus it will form COH, and COH, 1 electron, 1 proton reduction, it will go to the CO. So from this in situ measurement, like drift analysis, you can see that 1314 and 1509, it is connected that the monodentate carbonate, and this is the 1509, this is the bicarbonate species, and 1620, it is the COH, that's after the first electron reduction, and then you can get this CO, this corresponding CO at 2060. This is, you can understand that how reaction mechanism is happening. So then finally also we perform that free energy calculation, and then what happened from the ruthenium, after that reductive quenching, the electrons goes to the bipyridine, and then second electrons goes to the rhenium. Rhenium 1 become the rhenium 0, then oxidative addition of the carbon dioxide it happened, and then 1 electron it goes to the COH, and then CO, and corresponding release of the CO. So this is that whole process is happening, and throughout this and we found the CO2 binding is the rate determining step. Okay. And this we also got the oxidative addition product, and this oxygen we have removed, and this was the something that we can mimic the photosynthesis process, that converting the CO2 to solar fuel, and we can get that the oxidative oxygen as that oxidative product. Fine. So then next we thought, okay, if I take the same materials, so instead of taking some sort of that ruthenium, which is that some sort of the rare material, particularly the rare metal ion, so if we can take simple 2 donor acceptor complex and the same MOF, we can encapsulate, and how we can change the that what I told previously, that if you increase the electron density into the catalytic side, that you can get the higher order product. So for this, we have taken that particularly, let's say, pyrene. Pyrene, all of you know that electron-rich molecules, and when in the confined space, you can take the electron-deficient molecules, here let's say the methyl halogen kind of things, and you can make the complex. So there's a HOMO of this donor and the LUMO of these acceptors, that they can form the complex, the charge transfer complex. And this charge transfer complex can show that low energy visible band, and also the exciton binding energy will be less, because we have taken to electron rich and electron deficient system. So for this, we have taken this the mesoporous MOF, I told you, because it can either you can create the defect, as well as you can have the fissile diffusion, some sort of the substrate. So previously I showed that the microporous materials, we have taken the mesoporous material, same zirconium 808. So now covalently connect with this pyrene butyric acid, same principle. We have removed the formic acid and then pyrene butyric acid. Then cofacially, we can take the methyl halogen. So now we have the donor acceptor kind of arrangement, and this low energy visible light band, there will be some electron, and the electrons will come to the methyl halogen, and corresponding it will go to the zirconium cluster. So this is the characterization mesoporosity you can see from this N2 absorption isotope, and when you take the post-synthetic modification, it further decrease, and corresponding also into absorption and port size diagram, you can understand this. And also the high resolution TM also suggests there is some sort of the bright spot, that there is a the defect in the structures as corresponding, it suggests there is a mesoporosity. So then photophysical properties, when we just take the pyrene butyric acids, because of it forms very featureless emission, which is due to the exemeric emission. And exemeric emissions also supported the lifetime measurement. When this you can see there is a 23.2 nanoseconds, the lifetime when you have the methyl halogen. When you add the methyl halogen, the emission significantly quench, and corresponding the lifetime also decreased to 1.12 nanosecond because of the electron transfer in the, or charge transfer in the visible state. So that also then we have done the donor and acceptor positions, and this the LUMO level, it can go to the BTC and transiently it can give the electron transfer to the zirconium clusters. And this is the band structures corresponding this CO2 to CO, it is possible, or even CO2 to CH4, it is possible from the MOFs analysis and corresponding the band structures. So then we perform the photocatalytic CO2 reduction, and what we essentially we have understood this. We got that 8 electron 8 proton reduction. We got CH4 around 7.3 millimole per gram. Okay, so this that from earlier, when you take the ruthenium bipyridine and the rhenium is the catalytic side, we got the 2 electron 2 proton reduction. But we have performed in the aqueous medium in the presence 1 benzyl 1,4 dihydronicotinoamide in presence of the TEA. So when it gives that 1 electron, then it forms that cation, this radical, and then TA take abstract the protons because of that, otherwise there is possibility of the back electron transfer, and then it dimerizes. So when it dimerizes, that it is the reducing capabilities further increase. The oxidation potential of this BNAT is 0.57 and it is lower than this TA, which is 0.67. So even in this case, that this when it's dimerized, it further reduces. So and this kind of the dimerized product we have studied and we found from the LCMS, and it is 0.29 or 0.27. This the oxidation potential. So under the SC. So this strong reducing power, it can quench the hole efficiently, and we can get the higher order reduced product. So this is when we have covalently integrated, but when just in the methyl halogen and PBA does not show the catalytic activity. Okay. So then that in the ambient condition, there is the electron transfer. When you have done the EPR in situ by shining the light, you can see there is the zirconium 3 plus as that 2.01 from the EPR study side, and corresponding the methyl halogen radical cation also corresponding peak also it is increased. But when we perform in the just dark condition synthesis, there is no EPR signal. So that means the ambient dilate condition is sufficient for this charge separation in this material. Okay. So then further understand that the electron transfer kinetics, we have performed the transient absorption, and you can see the ACE band around this 400 to 450. It is spiral cation radical, and this broad feature 500 to 700. It is methyl halogen cation radicals. Okay. So then this is the transient decay, and particularly that from this methyl halogen that T average is 507 picosecond, and that there is a distinct decay time for both these cases. There is a no energy waste back electron transfer is happening. So when you don't have the MOF or you can make the physical mixtures, you cannot see this kind of thing. So the close that MOF and the covalent integration that can come very close proximity, and then you can see this kind of the feasibility of the electron transfer. And now, so this is the overall. So this pyrene butyric acid give the electron to the methyl halogen, and methyl halogen give this to the zirconium cluster, and corresponding catalysis is happening. So then in situ drift studies, this is the 8 electron reduction process, COH-CO, CHO, CH2, CH3O, CH3OH, CH3 and CH4. All that band corresponding the fingerprint bands we have able to isolate. So it is the CO, then you have the COH here, then COH, that you have the CH3O peak corresponding, and also the CH or the CH4, CH3 corresponding the CH stretching frequency, or you can get this. So now then we have done the free energy calculations, and so first the zirconium, take the electron by the BTC, and BTC again zirconium becomes zirconium 3 plus, then oxidative addition happened to the CO2, and then that if you also we have performed that CO desorption versus also the CH4 methanol formation, and you can see it is the much more exergonic process compared to the CO desorption, and it is corresponding go to the higher order reduced product to the CH4. So then it is the so this is the whole electron transfer process. You have the so you have this the donor and the acceptors, and then it goes to that, and this is the total other process, and it is happening like this. So Then we thought, okay, that as I mentioned, can you, one of the issues that direct electron transfer from this linker or the photosynthetic modification to the zirconium cluster, it is sometimes it is difficult. So is it possible the photosynthetically modify the clusters? So my student Somo, he tried 2 years and he found that on the iron 3 plus, you can one of the zirconium or one of the 6 zirconium center, you can replace pre-synthetically by the redox active iron 3 plus. So when you have, then you can photosynthetically add the same as I told ruthenium tris bipyridine. So then instead of that, through the BTC electron transfer happening to the zirconium side, it can directly give to that iron 3 sites electrons, because the LUMO level, alpha LUMO level, the iron 3 sites can be lower. So then because of the, you can induce the asymmetry, redox asymmetry in the catalytic side. Now here with the zirconium and the iron 3 sides, you can have the CC coupling and you can get the liquid product like the ethanol. So in this case, we can get the 1.2 millimole of the ethanol and small amount of the methanol. So I'm not going details, but we want to emphasize that we have done the drip and we are able to understand that all the intermediates. We want to highlight first is the CO2 binds to the iron site. Okay. So then iron site, it is becoming the COH. Okay. So then COH, then second CO2 binds to the zirconium sites. Then it is goes to the COH, then CO, COH. Then it is becoming the CHO. Then it's forming the CO. So then there will be COCH3 insertion. CO insertion into the CH3. So COCH3 it forms. This is CC coupling. And this intermediate we are able to get from COCH3. And then COCH3 corresponding the further reduction. You can get the 12 electron 12 proton reduction to the ethanol. Okay. So this, because of the redox asymmetry, you can introduce the same MOF by putting that one of the zirconium side, you can remove it. Then further, we have done the changing the light harvesting moiety from the ruthenium to iridium side. So iridium side, the PPY ligand, because of the strong sigma donor, there is a huge change in that the crystal field splitting parameters, and you can have the higher lifetime of this excited state. So when you have the higher lifetime compared to the ruthenium into the excited state, that you can see the electron transfer, it is going to the zirconium clusters directly, and you can modulate that the electron transfer pathway. So either you can take you have this iridium, then iridium, or you can have the cobalt one of the bipyridine. So when this from the iridium center, the electrons is going to the zirconium cluster, we are getting the 8 electron 8 proton reduction to the CC product acetic acid, and when you have the iridium to the cobalt acetic, you can get the CO. There is a direct electron transfer from here. So you can modulate by the electron transfer pathway, and you can get the product selectivity in the CO2 reduction. And you can also further, let's say the hafnium MOF, just a recent one, so that you can get the liquid product by photosynthetic modification nickel side to the clusters, and you can get these things. Okay. So I have another 7-8 minutes. So I'm not going this part is the methanol. Okay. Then this is the cerium work. So this. So now I will move to the photosynthetic modifications, how you can split the water. That earlier I saw the CO2 reduction to get some sort of the different product, either C2, C1 product, 8 electrons and 12 electrons you can do by changing the different way. So how that same MOF you can use by the photosynthetic modification to get and split the water. So here we have changed the strategy. Again, we have taken the MOF 808. So we have taken that one of the amino acid, cysteine. Okay. So photosynthetically modified again here, this cysteine residue. So SH, that NH3 plus. So we have used the soft site here. So soft site, it can bind the cadmium, lead, and mercury. So it can capture because of the soft interaction. So then when we have changed the cadmium, so if you just heat at 60 degrees centigrade, because this amino acid break and it can form the cadmium sulfide. So cadmium sulfide is a good semiconductors, okay? And this 1 to 1.6 nanometer small particles you can grow inside the MOF. So this is that confinement methods, not inside or outside. So then you can see that you cannot see the particles inside, outside. Only you can, when you do the high resolution TM, you can see that particles, very small particle 1.1 to 2 nanometers inside the MOF 808. So then 1.2 nanometers particle we have synthesized, and we have physical mixture with the cadmium sulfide. So when we perform the catalytic activity, let's say 4% of the cadmium sulfide, so the hydrogen evolution rate is very, very high because it is around 11 millimole per gram per hour. But when you just take out means the physical mixture, you can see that cadmium sulfide, it is agglomerated already outside. So that the hydrogen evolution rate is very, very small. So the close proximity between that catalytic site, the zirconium 3 sites, and that you have this cadmium sulfide semiconductor, it's significantly enhanced the electron transfer kinetics and corresponding the catalytic activity. Okay, so that really matters. And if you can see, after the multiple cycles, there is nothing change in, there is no leaching of the cadmium sulfide. But here you can see there is a leaching of the cadmium sulfide outside the surface. So this means the confinement effect is very, very important to make such kind of catalytic activity and through the post-synthetic modification. Okay. So I came to the final part. So this is the recent development in the group. So that photo and piezo-catalytic way, that same MOF we have taken. So try to understand that how you can create the asymmetry in the structures. Okay. So this is the cerium MOF 808 we have taken instead of the zirconium. So that is our design principle. And I will tell you how it helped the cerium MOF, and you can get that photo and photo-piezo-catalytic water spreading for the hydrogen evolution. So already you know the piezoelectric is a property of the ferroelectric materials to convert the mechanical states into the electric voltage known as piezo potential. So when you can, this is the unsteady state of the materials. So you have the non-centrosymmetric structure. Yeah, when you apply the compressive stress, you can get the net polarization, either compressive or tensile strength. And when you can develop the piezo potential, and this piezo potential depends upon the delta, which is the applied state, length of the material, and D, you can get the piezoelectric coefficient, and then relative permittivity R and epsilon 0 permittivity of the vacuum. So when you can generate the intrinsic piezo potential in the systems, that will help to make the charge separation in the material. Okay. So there is a debate what is the mechanism. So there's a two different kind of theory. One is the screening charge effect. So you have the unsteady state, and then when in that kind of piezoelectric material you apply the stress, then you will get the charge in the surface, because let's say the semiconductor, there are lots of free electrons, and when you polarize that, there is the screening of the charge happen. So you will get the charge negative and the positive charge onto the surface based on, let's say in the semiconductor there are lots of free electrons that can be now screened under this, that due to the presence of this polarization state, and that can help you drive the reduction and oxidation in the piezo-catalysis process. But another theory is the energy band theory, like that in the semiconductor you are applying the light and you can get the electron and hole. So unsteady state, when you apply the state, you can get the steady state where there is the bending happen, and that bending will give that there is some kind of the free electrons, that state will give the electron and hole, and you will get the reduction and oxidation. Okay. And in the ultrasonication state, there will be the formation of the cavitation bubble, and when it will go to the critical size, there will be implosive collapse, and during that time there will be it will generate the high local pressure, and this local pressure will help to generate that your electron and hole in the piezoelectric material. So this is the mechanism, and you need the non-centrosymmetric structure, and you need the non-zero polarization under the stress. Okay. So in the piezo-photogenic effect, so when you have the photocatalysis, there is always the recombination of the charge, recombination of the electrons and hole. But when you have this, the you can have the such kind of the state when you have the piezoelectric, that the state it will be the lower recombination. Okay, based on the photopiezoelectric effect, because of the enhance that inbuilt generation of the piezo potential, it will help further charge separation, and it will help the lower recombination, and you will get the synergy. So synergy equals to photo K photo piezo minus piezo versus K photo by K photo piezo into 100. So this will get the synergy, and then due to the sonication process, you can get in presence of the light, you can get the photo piezo state, and you can get the good catalytic activity. So we have done the cerium MOF here, cerium MOF 808. So first what we have done, we have, instead of that, earlier I showed the pyrene butyric acid, here we have the methyl viologin, and connected with the same the format linker photosynthetic modification we have done here. So then here we have taken the pyramid, the donor acceptor systems. Okay. So when you have this, there is a papers, I am not because of the time that, so in these clusters, whatever the global structures may be centrosymmetric, but the local structures that will be the, because of the presence of the many oxygen atoms, there will be repulsion of the oxygen atom because of the negative charges. They create the asymmetry in the structures. There is a paper in chemistry of materials, particularly the MOF 60AS, EYU 66. So when you have like this kind of the clusters, so because we have taken the cerium, because cerium has the low line 4f orbital, cerium 4 plus. So when it can easily get the electrons and it's become the cerium 3 plus. And when you have the cerium 4 plus 3 plus, there will be the significant change in the bond length. And then change in the bond length, it will be, you have the change in the local structure. You can create the asymmetry in the structures. And when you have the donor acceptor system, visible light, charge separation, so methyl viologin, pyrene to methyl viologin, electron can go even in the ambient condition. So now that crystal, when this is the clusters, which is the octahedrals, there will be some kind of the distortion in the clusters. Okay. So that whole thing, the city band, it comes, and this is the APR in the ambient condition that suggested there is some sort of the charge separation. And you can go, there is a see that from the pyranine to the methyl viologin cerium cluster, electron transfer is possible. Then we have done the Zens, and then we fit. When in the ambient condition you prepare, there is already 38%. You have the 38% of your. I have just 1 minute. I'll take couple of minutes. I'll take. So this around 38%. There is a change from cerium 4 plus to cerium 3 plus here. Okay, in the ambient condition. But when that you have the original cerium MOF, there is a maybe 3% of the cerium 3 plus. And when you have the light, there is you can see there is an increase and the cerium 3 plus formation corresponding the in situ APR study it suggests. Okay. So then we have done the MOFspace analysis, and then when we have done the band energy levels, that conduction band at the NHE 0.7, H₂O hydrogen it is possible, it is the minus 0.41 volt. And when H₂O 0.8, so it is possible, feasible for the splitting the water to get the hydrogen and the oxygen. Then we have done the details analysis by the exaph analysis we have performed. So if you look at after the photosynthetic modification, before that cerium, when you have the 2.60, so this part, okay, cerium oxygen is the BTC connected to the BTC, cerium oxygen bond length is 2.60. Cerium oxygen format is 2.60, and it is also there is a in the state. But when you have like the cerium oxygen cluster post-synthetic modification you have done, there is a change in the structure. So this means there is a some cerium oxygen bond expansion and some cerium bond there is a contraction. And because of this contraction, there is a some kind of the tilting into the octahedral geometry of the cerium cluster, and it is become the distorted. So that you create the asymmetry, and this asymmetry also we have performed by the second harmonic generation, and this has been done in Poland, the Jan Jareba's group. So this, and you can see that there is some cause of the when you have 1400 lasers, we get the signal at 700, that there is a local distortion in the structure, so it can be visible from this. And then we have done the PFM, and you can see there is a contrast that we get the two different phase, and this contrast, and this is the phase images. There is a 180-degree signal, and this amplitude image, this butterfly loop also suggests. And this cohesive field is 15 this we have done that 15 total plus 15 to minus 15. So this PFM very responsive, this is suggests is the piezoelectric material, and then we have performed the water splitting reactions, and in presence of the different we have done time dependent many way. So when you have the ultrasonication plus light, it is you can get the 80 millimole per gram around in 6 hours. It shows around 12 millimole per gram per hour, and it is also active with the only the light, only the ultrasonication. But when you have the both light and ultrasonication, because of the piezophotonic effect, that you can get the highest activity of the hydrogen evolution, and corresponding you can get the oxygen revolution reaction. Then you can see the quantum yield, that when we have done in the visible light and the CT interaction state, that quantum yield is very high in this state. And then we have the control study, frequency, and the frequency as well as the strength of the sonication. So different watt. So then with that we have 200 watt and 80 kilohertz is the optimum value, and where we get the highly efficient activity. So then we have done the cerium MOF is not good. Cerium MOF, only the methyl violin is got, but when we have performed the cerium MOF methyl violin, that endorse that the charge transfer interaction is very, very important. And it is the comparison table, because only handful of examples are reported, and we have reported the highest activity in this water splitting in the catalytic state. So, but when there is a no covalent interaction, you just confine the donor acceptor, there is no distortion is less, the catalytic activity is less. Okay, so the distortion made by the photosynthetic modification is also very, very important. Then isotope labeling experiments we have done with the D2O or H₂O 18 to understand the split the water to get the D2 as well as the 18 oxygen and stability, and try to understand that how it is happening. First H₂O2, then it is the OH. So this is the OH and terephthalic acids. It forms this kind of the E-CIPT band you can get, and O2 dot minus radical you can trap by the DMPO. You can get corresponding signal. So these are the and this is total how it split the water. So H2H plus 2 electron H2O, and this H2O dot OH H plus O dot H plus, then you can get the O2 minus 2H plus, the OH radical event. Okay, this is the corresponding mechanism, and you can get this one. So that in this talk, what I wanted to show you that MOF is a wonderful platform for the post-synthetic modification, and you can introduce the molecular level either light harvesting moiety or the catalytic centers. So you can make the close proximity, you can tune their electron transfer rate to get the different product. Either you can take the organic donor acceptor kind of systems, you can have the electron transfer channel to the catalytic activity, you can get the higher order CO2 reduction product. You can tune that by changing the light harvesting moiety and the catalytic side. You can get the 8 electron 8 proton reduction to acetic acid to 2 electron 2 proton reduction to the cobalt. You can get the CO production. You can post-synthetic modification MOF. You can get from the OS to good systems like the cadmium and you can make the cadmium sulfide easily and you can get the water split the water. And we have shown the same material by the cerium. You can make the donor acceptors, and you can introduce the asymmetry in the clusters, and you can get the piezoactive materials. And photopiezo by the synergisty, you can get the highly efficient catalytic activity for green hydrogen productions. Okay. So I would like to thank my students, because I just get this wonderful platform to talk, but these are these students, they work really hard to do this reaction. This work started by Sanchita, and then some of this work done by the Soumitra, then this Somo, and last work done by Audrija. So she is currently in Germany as a postdoc. Okay, these are the different places in the group. So I would thank from the different funding agency, particularly the JNCSR, CSR, ACRB, TST, Government of India, and that we have the National Supercomputation Facility in our centers. I gratefully acknowledge them. Then DAISY, Germany, we go for the particularly EXAFS and ZENS studies. And we have the different collaborator for this TA study from BARC and TIFR, and some of my colleagues, they also helped me the theoretical calculation. And last, I just want to share this, and I close. So this is the Nobel Prize interview when Professor Kitagawa gave. He told, don't switch off the light even at night. And when I was working in Kitagawa's lab, I found I did not say that in his lab, light switch, because many students used to work whole night. So, but the true meaning is that different. The never switching off the light represent continuous curiosity and persistent pursuit of knowledge that drives breakthrough discoveries. And thank you very much for your.
Thank you, Professor Maji, for this interesting lecture, for valuable insights into design and structure property relationships of MOFs and other porous materials. Now we have time for some questions. So if you have a question, you can raise your hand or write the question in the chat as you wish, please. Yes, please, Kenichi, you can ask question.
Yeah, so nice to meet you. Thank you very much for this nice presentation. I'm very amazed the variety of the systems you built from this one MOF H₂O. And my question is about this piezo-catalysis, because I think this is a relatively new topic. With this synergy between photo and piezo-catalysis, do you actually increase the energy efficiency, or is it still not as high as the pure photocatalysis?
Yes, it is indeed, because we found that is the 60% synergy. So when we have done without only, let's say, by in presence of the light, and it is just only the sonication, mechanical perturbation, the efficiency is not good. 3 millimole per gram per hour, or 1.5 millimole per gram per hour with the light. And it increases with the presence of some sacrificial, but it is increased 12 millimole per gram per hour. So yeah, that it does that when you shine the light and you have this perturbation, that you can see the efficient charge separation.
So but I mean,
really help for that synergy. Yeah.
So if you increase the energy you need for sonication, is it still better compared to putting all the energy to the right?
No, because this is the optimum, that your frequency as well as the that light is that source also is optimum. So we have done the different control study, and we found that 200 kilohertz is the optimum frequency for this catalytic activity with the 200 watt.
Okay, thank you very much.
Then we have, but we did not change the intensity of the light.
Okay, so it's still depending on the material.
Yeah, yeah.
Thank you.
Okay, thank you. We have one more question in the chat. So thank you so much. Since BNA-HTEA seems important for the carbon dioxide reduction performance, what controls help separate the framework confined charge transfer contribution from the donor-driven redox chemistry?
I have, can you just one more repeat that? So,
Evelyn, you want to? Okay, you will be the next one. Okay, I can repeat. It's in the chat, this question. So since BNA-HTEA, I think tritilamine, seems important for the carbon dioxide reduction performance, What controls help separate the framework confined charge transfer contribution from the donor-driven redox chemistry?
Okay, so if I understand correctly, the questions is related to the pyrene donor acceptor complex. So we have used the pyrene butyric acid as the donor and that pyrene moiety, chromophoric moiety, and that methyl violin as the acceptor. So when you have this confinement effect, the close proximity, you can have the donor acceptor and efficient charge separation because of the coefficient arrangement between the donor acceptor, and that it helps to the electron transfer channel to the catalytic side. So that we feel the confinement effect is the very, very important. And when it is done, that we have also done the exciton binding energy calculation. I did not show it, that exciton binding energy is very, very low for this because of the donor and acceptor, because two different electron donating and the accepting capability. That also plays a significant role for electron flowing to the direct, the zirconium cluster.
Thank you so much, Dr. Maji.
Okay.
And can I ask one more follow-up question, because that was my original question?
Yeah, please.
So I was actually curious, why did you select the BNAH as the sacrificial?
Okay. Sacrificial electron donor. Okay, BNAH.
Yes.
So BNAH is the 1-benzyl 1,4-dihydronicotinamide, and we have used for this, if you show that the oxidation potential of the BNAH versus TEA. So it is the low oxidation potential. So it has the higher reducing capability. So when it gives the one electron to the, when it is the reduced, then after giving the one electron, it forms the BNAH.H plus. So then we use also the TA, it take up the H and it is called the BNA dot. And this BNA dot, it dimerizes and it forms the BNA2. And BNA2 at the oxidation potential further reduces, it's become the 0.27. Okay, volt. So that means it is much better reducing agent. Okay, and we have done the LCMS study. So when that means that it will be further. So that means that when it is that efficiently quench the hole, that it can help to get the electrons to the catalytic site much easily. So that we can get the higher order reduced product. That is we have done. And it is that the BNA radical dimerized, and we have studied LCMS study, and we can found that it happened at the BNA, and that helped for the efficient, the reductive quenching of the hole.
Thank you so much.
Okay, and we have a question from Evelyn, please.
Okay, I have actually three very short ones. So first of all, thank you very much for this very cool talk. So if I take MOF-808 as a scaffold itself, I was wondering, first of all, the impact of water itself on the structure, on the stability. And if it's stable, how would you, let's say, do you modify it before so that it stays stable also over time? And if you have basically the stable scaffold, modified as ever you wish, what is your most favorite metal in this sense? Do you use a specific metal for a particular reaction? So how do you choose these components?
So this is very important questions, and let me just clarify. So MOF, that as I told, that this is the wonderful, particularly the 808 side. So we use this platform because of the high stability, and you can create the defect. You can size the particle size, because 500 to 50 nanometers you can do. So these are the, and it is the most important things, it is the much more stability. So when we have, let's say, we have done the pre-synthetic, we tried that one of the zirconium side to different metal ion. We are not successful. Only one success we got with the iron 3 plus. Okay, so that, but one metal side. So we are trying to make it the 2 metal side, but it did not happen so far. Hopefully we'll be able to. So iron 3 plus, because we saw there is a change in the morphology when we have changed, because of the coordination number 8 versus 6. So that is the challenge. So one, but because we wanted to create the asymmetry, because the proximity of the two different, the redoxide iron 3 plus and the zirconium 4 plus. So that when you create, then you can get the CC binding and you can get the high rotor product. That is the one. But that when you have the different hydroxo and oxo group, even that you can connect the some transition metal ion, like we have done the nickel post synthetically. So then you can make the light harvesting moiety where we can see that product can be methanol. But our that approach, that another approach, that change in the format linker with that similar carboxylate group, like then we can put the ruthenium bipyridyl, iridium bipyridyl, like the bipyridyl side. That will help you to give some molecular, like the homogeneous, let's say homogeneous catalysis well known by the ruthenium and the rhenium. But these platforms give you to make the heterogeneous catalysis based on the molecular system. Like we have the ruthenium, the light harvesting moiety, and rhenium. So now you have the close proximity. So close proximity, when it is there, you have the faster electron transfer to that in the inside the pore, and you can get the efficient catalytic activity. So this way MOF gives the wonderful platform of this kind of post-synthetic modification compared to the homogeneous catalysis, particularly the impregnating of the molecular light harvesting moiety as well as the molecular catalytic side, like the ruthenium, iridium, we have done manganese, rhenium, so many other things can be done.
I see. Thank you very much.
Okay, we have one more question in the chat. Can the concept of post-functionalization be applied to generate hybrid catalysts using MOF as the solid support for organic reactions like CH activation or reductive N methylation? Can you comment on its use as a photocatalyst and also its scalability and stability? It's a question from Norsang Tamar.
So yeah, that is the very important questions. Indeed, there are quite a number of reports that post-synthetic modification, CH activation, or the different type of organic reaction like amidation, different organic transformation already people have done post-synthetically, or even that electrocatalytically, that some people are trying to do the urea production, CO2, then the ammonia reduction, then CO2 plus ammonia, or from the nitrate reduction that people are trying to make it. So particularly that we have chosen this platform, the MOF 8.0. One of the reason is that it has the high stability. And as I mentioned, the high stability comes from the zirconium 4 plus, which is oxophilic, and it forms a strong bond with the oxygen. And then it forms the clusters. Like we have that zirconium hydroxo-oxo clusters, and it is the BTC, which is the oxygen ligand. So that gives the stability of this material, and which is very, very important for this, particularly if you want to study. We have studied, let's say, after catalytic activity, some cases 7, 8 to 10 cycle. And we found after the post-catalytic characterization by the TM and other way, we found this material is particularly very stable.
Okay, thank you. More questions, please. I don't see questions. Okay, Stefan, yes.
Can Tapas, I would like to ask your opinion for the next hot MOF and COF topics of the future. Now, because we have now the Nobel Prize. Okay, COF is a bit easier because they didn't give for the COF, as you're well aware, I guess so. But for MOF, it's harder. So, what do you think for the younger researcher? What are for you hot direction for MOF research the next years?
So MOF, I feel that the next breakthrough should be the some sort of the MOF-based composite materials. I feel that will be the wonderful research direction. Not much explored like this. Let's say if you have the covalent integration of the MOF with another material. Let's say some research is done like the graphene, MOS2, or the WSC2, many kind of material. So this will be the wonderful material, particularly this one field which I gave a talk. So you will get the very interesting, because I feel the interfacial electron transfer Stefan, it is a very interesting topic. How that when you get the interfacial between the two components, how the electron transfer play the role in the efficiency and understanding also will be the very interesting to study. I feel this particularly in this field will be the wonderful to study, because this is not known how it is going to have that the interfacial electron transfer. And one more field that particularly I still feel the MOF has wonderful can do still that biomedical research. Biomedical research still there is a potential to contribute in the MOF.
And what do you think about, especially from India, what do you think about the water harvesting and
water harvesting will be that as Professor Yagi already showed that there will be significant.
Solved, but
again,
still there's a lot of.
I think in not again I told the composite material, which some sort
I
of
believe
will be very good for the water harvesting. Maybe efficiency.
I totally agree.
Some sort of the like you have this very hydrophilic material and the MOF. If you can make the composite, that will be wonderful material for the and people trying to make it such kind of material.
Yeah, including me. I mean, the composite at the end it's a bit dirty business because you mix, you cannot make so nice crystal structure and this chemical design. For example, Omar, I don't know Susumu, but Omar doesn't like it. But at the end, for application, MOF application, I strongly believe in MOF composites. Strongly. This is
I feel that also. And it will be one, you can covalently link also, because you can modify the surface and you can connect the covalently. Okay?
Yes.
So that will be very wonderful, that things, because it fascinates me that when I look at that just really, so it is not 1 + 1 = 2. It will be 1, 1, 11, 1 + 1. So
yes,
that will, because that's the synergistic effect of the two different components. It's really wonderful to get the new material. I think this is the.
Okay. Yes, I agree.
Okay, and we have one more question in the chat. I will rephrase it a bit. So, why did you use cysteine for post-synthetic modification? And is there, if to take methionine to obtain cadmium sulfide MOF 808?
I don't know why did you use? Why did I use?
Yeah, as I understood, the question is why did you use cysteine for post-synthetic modification?
Okay. Suppose that is because we wanted to make the soft, because cysteine when you are binding that carboxylate bind to your plaster. Now you have the sulfur SH and the NH2 group. This is the soft donor center. So it can connect with the soft metal like the cadmium, lead, and mercury. It can easily capture it. So then we found one literature that kind of cysteines when it connect in the low temperature, like 60 degrees, you can make one of the way to prepare the cadmium sulfide. We found. So that is that in the literature we did not know. Then when we found that that cysteine can be the cadmium sulfide, then we can confine the cadmium sulfide by heating inside the MOF. And that the confinement, very, very small particle we have used, and then we have done the water splitting. The idea is the soft metal center we can bind, which can means your OS2, you can get the good material. Like you can cadmium you can capture, and then you can make the catalyst. That is the whole idea.
Okay, thank you. So maybe more questions? No? Okay, thank you again for a nice lecture and for answering all our questions. Yes, thank you a lot for accepting our invitation and for being with us today. And I want to thank also to all our participants for their patience, yes, and for being with us today. So with that, I want to wish you all a nice day, and yes, we look forward to seeing you at our next MOFspace webinar. Thank you.